Hello. Shall we start?
Go back in time and start 5 minutes ago.
Alrighty, so hi, I'm Brad Nelson. Here to present fourth haiku vision. So a recap for those of you who have missed all of my talks for the last, forever. Fourth haiku is about creating tiny programs that are beautiful, and in particular, this is accomplished by taking small fourth programs and compiling them to compiling those programs to JavaScript, and then doing a conversion to a GLSL shader. The idea is that you can share and evolve these programs on the web. So quickly running through the basics, you've got a small word set of fourthy words, but with the somewhat unusual caveat that those fourth words manipulate floating point numbers. And the idea is that the program runs once for every pixel position in the image. And there's some special words, X and Y, that provide the current position so that you can take that into account as you specify the program. And then the state of the stack after one run of the program is the red, green, blue, and optionally alpha values of the image. So this lets you take something very small like this and turn it into something impressive like that. Of course, so this was sort of the initial version. In fact, this was actually the sort of thing that you could do just with JavaScript. But of course, I wanted to do more. So over time, I've expanded the language in various ways. And the trick is, of course, because this is something that's being edited by folks live on the web, I want to thoughtfully grow the word set in ways that I don't have a compatibility problem and I don't break existing programs that are out there. And another constraint is that, especially as I've gotten into more advanced features, I'm constrained by what WebGL can do, and so I have to work within those limits. And so that's why this is a somewhat eclectic variant of fourth, and is not a more conventional fourth, because I'm operating within the confines of the API that I have for doing fast display and rendering on the web. And so I've tried to add a small number of very powerful words rather than an exhaustive collection of graphics words or something of that sort. So the next thing I added, let's thinking through sort of how this has evolved as animation, and this was done primarily by introducing T for time. And so then you can take into account not only the position that you're at within the image, but also a rolling time value. The time is specified in seconds since midnight, primarily to allow for the possibility of a clock that's actually synced to the present, something like that. And indeed, well, that one's got a sub-second hand. You'll notice something I started relatively recently doing is tagging the different categories of haikus depending on their word content with an icon. That one's got a little TV because it's animated. I had been using a camera actually until just this last week or so.
Is this the current time?
It should be, and let's see. Oh dear, yeah. Yes, it should be the current time. So yeah, it is in fact. I had been using a movie camera actually as the icon for animated haikus. There's also some other iconography, but I recently switched it to a TV because I want to use cameras, as you'll see in a moment. Of course, I've been astounded by what people have been able to do with this. A tiny program like this is able to create something like this that I would have never imagined that folks would have been able to do in that little code. So another thing that I explored adding was interactivity. This was actually circa the last fourth day, in fact, that I first really actively dived into this. I introduced 4 words, MX and MY, for the mouse position, so that way you can know where the mouse is at relative to the display. And then I kind of regret this in hindsight, but I have two separate words, both buttons and button. One of them provides a single value that contains bits turned on and off for a set of buttons on the keyboard, and button provides a query. You pass in a number for which button, and it returns a 0 or 1 to indicate whether that button is pressed. And you'll notice that the theme with these words is that because they have to operate within the confines of a program that is run over and over for each pixel position, they have a tendency to be based on querying information rather than sort of manipulating state. So this allows you to do interesting things. Here's one that is hooked to the mouse, and so depending on where the mouse is at, some parameters in this haiku change. I'm not going to bother showing the text for this one. It's a little bit more involved. And you'll notice that for these, I display a little game controller as the icon to indicate that they're interactive. And I've used, I should say, there's a few other embellishments I've made. I've had several different rounds of attempts to support sound. Won't go into it, but I will say that in some ways, images are actually far less challenging than sound. Sound is, it's very easy to make unpleasant sounding noises. It's actually relatively hard to make pictures that hurt. So there's a sort of this natural forcing function encouraging me not to do more with sound, although over the years I've tried various approaches, and there is currently an audio word that lets you do raw waveform. And for what it's worth, there are some features coming to the web that I won't go into as well that will make it possible for that to be performant in the not-too-distant future. But for the purpose of this talk, the thing that I wanted to explore is something people have actually asked about sort of directly and indirectly for some time, the idea of doing video input. Typically in the past when people have asked about this, they're usually literally asking either about video input, or they also will ask about texture input. And this is from the insight that underneath the ability to animate these is the fact that we're using the capabilities of WebGL. And WebGL operates on textures. So typically when people are using WebGL for 3D graphics, textures are par for the course, where it's extremely unusual that Fourth Haiku doesn't actually have any textures as input in terms of how people use WebGL. But of course, the constraint with this is that I am limited by what WebGL can do. And in particular, actually, it's only very recently that WebGL, and in particular WebGL 2, has gotten particularly adept at letting you bring in a media stream, which is the web's version of a video source, into a texture. There have been ways in the past that you could do this, but they were frequently relatively non-performant because you had to bucket bell yourself the pixels from one place to another. But basically now what you can do is fairly easily create a situation where the video feed coming in from a camera turns into a texture that's available to the program as it runs. So I'm going to talk through let me introduce you briefly to the world in which I've had to operate in order to make Fourth Haiku work. So unfortunately, because these programs run on the GPU, the way that the GPU works is part and parcel of the model. And so there's two kinds of programs that are under user control when you're running on GPUs. At least, by the way, this is the model that's present in WebGL and WebGL 2, which is a mirror of the models for OpenGL ES 2 and 3. So the basic idea is that you have this programmable pipeline of things that can happen. And your app provides, and by app, this slide really means that the inputs coming from the CPU provides a number of pieces of information. It provides raw vertices, positions, and so normally, remember, this pipeline is used to do 3D graphics. And so you get a bunch of coordinate positions in 3D. You get connectivity information. So typically, you don't just have a bunch of points in space. You have a set of triangles that are connected, or strips and fans of these triangles. You get textures, which up until now Fourth Haiku hasn't been using. And then you get a bunch of options in terms of the mode that the graphics pipeline is operating in. And the two main pieces of actual executable software you can provide are a Vertex shader and a Fragment shader. Now, Fourth Haiku has almost exclusively been a Fragment shader. The Vertex shader is an opportunity for you to take the vertices that come in, typically 3D points, and do transformations on them. And so this, in normal operation for when you're doing 3D graphics, is used to transform where objects are at in the world, to warp them in ways that reflect how a camera might do projection, this sort of thing. So anyways, what happens is you feed in raw points that are in a three-dimensional space. They're transformed in various ways, and out comes a set of transformed vertices. At that point, you do rasterization, and basically what happens is that those points and their connectivity information is used to assemble a bunch of points that fill in various triangles, actually in the space of the screen. And so for all of this plumbing in the context of Fourth Haiku, I'm simply providing basically 4 vertices, or actually 6 vertices, because I've got 2 triangles, and then those are not transformed at all because I'm not actually using anything 3D. They come through and then they're rasterized just as a series of 2 strips. So what you get are a bunch of fragments, which are just regions in the screen that are going to be drawn. And this is the point where so the GPU is able to do things massively in parallel. And this is one of the reasons you may have heard the GPUs are becoming very competitive in terms of performance, but only for certain kinds of workloads. They can do a lot of this vertex processing in parallel. But then the second thing that they can do in parallel is all of these operations in terms of rasterization. And so the individual regions of the display can be broken up and hand processed individually. And so this is where you get this big fan out. Typically, you'll have, to give you a sense, something equivalent to about 16 cores, but then it's actually even sort of faster than that, because typically what will happen is that those cores are able to very carefully orchestrate how they cope with caching, and so they're able to sort of amplify their effectiveness so that they're conceptually similar to hundreds of cores.
You will find that the number of each core will be able to handle 2 threads.
So these, bear in mind, this is I'm talking about the GPU distinct from the CPUs. The CPUs,
they're the same concept.
yeah.
So
it's similar. So with CPUs, you're able to do what's called hyperthreading, where you have a duplicate set of registers, and you're able to very quickly toggle the threads. With the GPU, one sort of similarity but difference is that typically you're running the same program throughout each of the different GPU cores, and so there isn't the exact same toggling of state. The other difference is that a lot of the bottleneck in the GPU would normally be waiting for data coming in from external memory, and so being able to round robin between a very large number of different fragments but it's very tied to this model of a fragment, and so that's why, unlike a CPU where you'd have diminishing returns, having hyperthreading times too many different ways, with a GPU you can get a win where you sometimes do 16x hyperthreading, that kind of thing, which you would never consider with a CPU, just because the CPU would be saturated long before you get there. Another key thing, though, that the GPU cores are able to do that's distinct from a CPU is that this texture data that I mentioned before that's coming in is going through a special memory unit that's specifically designed to do caching with the assumption that you're doing sampling from a texture. And so it has a lot of heuristics in it around the idea that you're going to pull out information sort of coherently as you stripe over a texture. So as you're pulling in some piece of texture that you've wrapped over a triangle, you're typically, as you're drawing that triangle, accessing roughly the same region, possibly at different levels of detail as you go. And in any event, what you have with a fragment shader is an opportunity for every single pixel to make a local decision about, based on where you're at geometrically, the textures that are coming in, and some ability to sample those textures, what color you ultimately emit. And that's basically, Fourth Haiku has lived in that place pretty much its whole life. And then at the very end of all of this, the frame buffer in GPUs also has a number of compute capabilities built into it, and so it can do various kinds of blending operations and different kinds of stenciling and use of buffers. And typically, that is also not used in 4th haiku, at least. There's all kinds of wonderful tricks you can play with it in general. So running through this again visually, right? You've got the points. They turn into they're assembled into triangles. They're rasterized. Each pixel is filled in, and then there's a shader decision in terms of the fragment shader to decide how to shade them. And I should say, by the way, normally the purpose of this fragment shader is to provide a description of how to texture how to wrap a texture around these triangles, like in a 3D model, but also to simulate lighting and reflection and all kinds of interesting visual tricks. So this is normally meant as a facility to offer sort of detail on the surface of a 3D model. But for our 4th haiku, we're using that sort of as the primary purpose. And the interesting thing is that because these GPUs have gotten extremely general, that's not as wasteful as it would have been in the past. Historically, this pipeline was all sort of custom silicon that had greater restrictions around what you could do with it. But the general direction is that each of the pieces of it has become more and more programmable over time. And so as they become more programmable, typically, when a fragment shader is executing, it's oftentimes sharing a lot of the same underlying hardware computing elements that would be used in the Vertex shader phase. And where historically, because fragment shaders often operated on texture data, they often had data types that were sort of texture-oriented, and Vertex shaders were sort of floating point and 3D coordinate-oriented. Over time, those have become basically the same. Both of them operate on floating point-oriented data, that sort of thing. So in any event, after much introduction, here is the new capability. I've added 2 words. This one is so sample. And recall that X and Y give you the current coordinate position. And actually, I'll just turn this around to face the audience. People can. Nothing has fundamentally changed about 4th haiku. At each position, you can ask the X and Y coordinate. But now this word sample, when given an X and Y coordinate, will sample the texture that's coming in at that position, and then give you the RGB value at that location. And so this program is just for each position, finding out where you're at, and then asking, give me the RGB values from the textures. I quickly discovered that this word is a little bit awkward, even though it's very general. And so I also added a second word. This is BW sample. So this just does a grayscale sample at a given coordinate. And for a number of operations that you might like to do to manipulate images, it's actually more interesting to get a grayscale, or it's not more interesting. It's frequently useful to be able to get a grayscale value. And one of the other nice things that this lets me sort of hide away the complexity of is that when you take an RGB value, and if you want to convert it to grayscale, our perception of red, green, and blue is not uniformly balanced. And so the correct way to yes, George.
He's watching me making.
Indeed. The correct way to combine those RGB values is to actually weight them with a particular set of 3 magic constants when you add them up. And by providing this as a built-in word, I'm able to bundle up that calculation. Whereas one of my fears was that if people started to use the other word extensively, they might constantly repeat over and over the description of these 3 constants. I mean, they're welcome to do that, but this allows things to be more pithy. So in any event, at this point, I'm going to actually transition into the app itself, because that's simpler in terms of showing off the various things that it can do. So the motivation overall, remember, was that I wanted to do interesting things with video. So now I'm just going to go through a bunch of these to give you a sense of the ideas that I've had. And I'm sure others will propose other things. So, I mean, obviously, the starting point is just plain video, and that's boring. So the next thing that was obvious is that I could take advantage of the ability to change where I'm sampling in the image to manipulate the coordinate system. So I'm at a given X and Y position, I'm perturbing my X and Y position both in time and space, using some sine and cosine curves. And I'm using t, where I'm I'm scaling it by 8, so it repeats over and over and oscillates. And that's all kinds of fun. But of course, let's see, what else can we do with this? One of the early things I realized, of course, is that you could do edge detection. And here I'm using the black and white sample where this isn't super obvious. I'm going to make that a little bit bigger. So the idea here is that I'm sampling at several different positions relative to the current coordinate, and then doing a subtraction. And I'm doing this both in the x direction and in the y direction, and then actually in a slanted direction to give sort of an RGB edge detect.
Aren't you just doing a high-pass filter?
It's a question. So I would say that it's distinct from a high-pass filter in the sense that I'm not actually doing anything in the frequency domain. I'm actually doing a sort of a nearest neighbor subtraction. Actually, that's a good question. Whether it's an interesting question whether it works out to be the same if it's high. Yeah, this is I don't think that works out to be the same because with a high pass filter you would there's not a again I think this is more like, think of this more like this is the derivative basically. So the derivative in x, the derivative in y. That's okay.
That's a high-pass filter.
Okay, that tells you how lousy my signal processing is. All right. So of course, then there's more possibilities in terms of coordinate mapping. You can easily create all sorts of funhouse mirrors and things of this nature. So that's of course an infinite joy. I imagine that over time all kinds of interesting things will happen. This was just me mashing together a bunch of different. This one's interactive, so clearly I have to make it larger so we can interact with it. So here, I see. So here I've got the center doing sort of I'm using the mouse coordinate to manipulate something similar to the effect that I did with the mirrors, but then I'm also overlaying that on top of other videos, so it's this kind of weird combined effect. Fairly arbitrary. I wanted to convince myself, and I should say, by the way, a number of these were informed by me trying to convince myself that I hadn't made any mistakes in the implementation. Here I'm doing some manipulation on the color of the image, and then I'm overlaying a cutout, and so you can see that I can make decisions locally to decide when the video peeks through or not. Of course, another option. This one I might actually let's describe this one in a little more detail because it's interesting. So here I'm pixelating the image, and you can see this very low-res version of things. And actually, I'm going to zoom in here so you can see the haiku. So here I'm just taking the x-coordinate, multiplying it by 20, flooring it so that I clip off the fractional part, and then dividing it by 20 so that I get a sample that's sort of rounded down over several pixels. All right, so this one's fun. I took that previous effect with the pixelation, and I combined it with, this is actually one of my favorites so far, weirdly. So I combined it with I combined the pixelation, and then I overlaid on top of that the difference filter. And so here you're seeing sort of highlights around the outlines of the edges of the shapes, and but you're also seeing that overlaid on top of the video. And so you've got this kind of weird Terminator type view of things. Here is again me convincing myself that the performance is tolerable, and so I've got one of the other haikus overlaid as a color filter on top. I've forgotten who this was derived from. I'm sure it says down below here. This was derived from a haiku called Ink, which I believe is from Manwei. So, in any event. Here's another one where I'm just manipulating the color space in rainbow colors. Here I decided let me try to really do crazy things with the coordinates. So this is it's hard. Actually, let me scale it up a little. This is just even more repetition of the same thing with that mirror effect. So spider eyes kind of thing. Again, here's my convincing myself that I haven't completely trashed performance. So I took one of the popular coffee haikus and overlaid it. Here I'm doing something dynamic where I float the view around, and so I'm just manipulating the coordinates so that the image moves around in time and space. Here was my attempt at a blur. So blurring is actually it's interesting the constraints of the haiku. And actually, let me blow this up a little so you can kind of see better. But the way that I had to accomplish a blur, which I'm not entirely satisfied with, is I'm really just taking several samples in proximity and averaging them. The trouble is that typically when you do a proper blur, you want to do this over quite a large number of samples, and you want to weight them appropriately. And the challenge is that each of the texture accesses is hitting that texture unit, and there's some limits as to what it can cope with. I haven't actually pressed those limits, but my suspicion is that if I took enough samples for a truly proper blur, I would probably be very disappointed with the performance. I also colored it to look like an old-timey photograph. So then here I decided, okay, now let's try to accomplish what amounts to a dither. And for the dither, I'm having to try to map the pattern, map a regular pattern, and then use some fixed set of rules to decide how to make the decision as to when something is on or off. And so this lets me do a very localized dither. This isn't sort of like one of these error diffusion dithers where I can spread the error out, because that sort of thing would be extremely challenging because remember, computing each of the pixels in isolation, so you don't have that opportunity to spread information around. Yes?
A movie done using this, although it was a black and white.
Indeed.
There was it was either gray. There was no gray. It was either black or white.
And in fact, actually, a lot of all kinds of printing over the years has used similar techniques. And actually, this is closer to something like what newsprint uses. Drawing a blank on what's that? Halftone. Yes. And there, the idea is that historically, it was an actual mechanical mesh of points, and then depending on you would spray more material through.
Yeah, it's like you take a superpixel that's made up of some smaller pixels, and then depending on what the density is, there's a pattern you put in there.
Right.
That gives the darks. I did this when I was working on APHIS, and where I had to print out fingerprint cards. The fingerprints themselves. That was fun stuff. See, now this is.
I'm excited to hear you worked on APHIS. I'm dying to ask you all kinds of questions about it later, but so here's an interesting variant I wanted to try. So this is actually also exclusively black and white, but here what I've done is I'm combining it with a random noise function per pixel, so it's effectively a higher res version of the other one, hence the static. So I'm taking a random value and then just doing a comparison and saying, is the grayscale value higher than this value at this pixel? And because the random value changes over time, we see this nice static effect. Here was me convincing myself that I could filter for something interesting or semi-interesting in terms of edge features, and then it doesn't actually look that great in this lighting, but I was able to sort of attach scudge all over things live, and that looks horrible. I don't remember why I pixelated it. Here's a similar idea to that static image, and I'm doing it once for each RGB channel. Actually, I'll show you one other thing in a second. Here's another overlay of a haiku just on top, peeping through the filter. Here's another colorful one overlaid on top of me. Excuse me. Here's one of the more lens flare-y type ones, again overlaid. And you can barely see me, but this is one of our tunnels with me inside my little semi-Doctor Who something or other. And that's a repeat. Another one of these, sort of me peeping through. Can't really see that one very well. So okay, this one. So this doesn't look like much at the moment. Let me blow this up though, because there's an extra trick here. So of course, another fun thing that people historically have done with use of color and filtration is Chroma Keys. And so I have this. So what I've actually done here is I've taken the camera and I've actually split the two down. You're actually seeing a combination of both the left and the right side of what's coming from the camera. To make this more clear, let me hold up this sheet of paper in front of the left side of the camera. So now this is filtering green, and so everywhere where the camera sees green on the left side, it's treating that as transparent, and then it's overlaying the right side of the screen. Where this gets interesting is if I have a shape in front of it, I can then overlay that shape on top of me and move that around. So, unfortunately, you'll notice that the quality of the chroma key is quite terrible. When people did this historically with film-based techniques, of course, they would spend tremendous effort to get the lighting right because they had to use analog techniques to make the decision about what color. When folks do this digitally, of course, they use lots of non-local calculations to figure out, okay, well, this is green here, and it looks almost green over here, so let me continue to treat it as green because I know it's continuous. And so modern chroma keys that don't have the constraint that I'm operating under here are able to do smarter calculations to cut things out. Whereas here I'm having to remember a local decision for every pixel. And so I can't know that the pixel nearby me was green. I could certainly do a little bit more local sampling, and it would probably increase the robustness some, but there's bounds as to how far that could go. Of course, I had to overlay Pac-Man on top of me, because, Pac-Man. Whee! So this is actually, this was one observation that you'll see frequently in image processing is that the human visual system is less sensitive to color spatially than it is to grayscale information. Now, I actually made it. So what I tried to do in this particular one is to demonstrate this. What I've done is I'm showing a pixelated view of the chroma information, but a high-res view of the luminance information. However, as you notice, it actually looks kind of sparkly on the edges. What I did was I made a little bit of an error. I was rounding towards the upper left corner of each pixel. And so you're seeing the chroma information sampled at the lower left corner, but spread out over the entire image. And so this doesn't look as good as it could. So I have a second version of this where I am instead sampling from the center of the center of it. And you'll notice that surprisingly, even with a fairly coarse grain, this is just 20 pixel by 20 pixel chroma, the images really don't look that bad. And it actually gets, if you changed it, oh, sorry, this is 40 by 40. If you change it to something like 80, for example, it gets even harder to tell, even at a fairly low resolution, that there's any missing information because our visual system doesn't care about that. And then this was just me needing a link for the black and white picture for the slides. So I wanted to highlight one other property of this. You'll notice as I go into this that there was that brief flash of the SVFIG logo. What's going on there is that, of course, the camera is not always available, and in fact, the way the camera APIs work, you don't actually instantaneously know whether you've yet got a stream feed. And so I'm going to click up in the corner. I should say, by the way, if you go to 4th Haiku now and you have one of these images up that needs the camera, it's going to ask you permission to access your camera, and you're welcome to say no. Also, you can, of course, click in the corner and block the camera. And if I reload here, now what's happened is that I've blocked the camera, and so in its place, I substitute a fixed texture with the SVFIG logo. I briefly tried having a canned video, but I found that I didn't have a very good canned video. The other reason, if others have suggestions, I'm welcome to entertain it. But the other reason I thought it was nice to do the SVFIG logo, aside from getting it out there more, is that having a fixed image is actually very useful. I'm going to re-enable this. It's actually very useful in terms of and you'll notice that there's that momentary delay before the camera starts. On a view like this, where things are fixed, I don't actually want to show the animation, and so I show the SVFIG logo, and then once the video feed is available, I show the camera feed. And the challenge is that if at least with the simple canned clips that I was able to find, I didn't like the first frame of any of them, and I would like something that sort of gives you a sense of the haiku. I don't really want to animate all of them because the GPU, frankly, can't keep up with that much work. If you float over each of them, it animates them individually. If I wanted to fix this, it's possible that I could on very good hardware, but what I would probably want to do is collapse together each of the haikus into a single giant shader. The GPU prefers that you keep the program the same continuously rather than you toggling it back and forth. But each of these is currently treated as a separate program. So there's one other thing I wanted to show you. The nice thing about this is, of course, I'm going to not close that so the camera doesn't turn off. The other nice thing is that not only does this work, on the desktop, but it works particularly nicely on phones. So let me do one. So I'll do Pac-Man here, and so as you can see, I've got Pac-Man overlaid on video coming out of my phone as well, and I can bring that closer to the camera if that's at all.
Oh, I see.
Yeah. So in any event, any questions? Yes.
Could you optimize that just to transfer get rid of the JavaScript level?
Possibly. So we got here kind of evolutionarily, and the conversion step to JavaScript was because my first implementation was in JavaScript and didn't have animation. And actually, at the time that I did it, I kind of knew I might try the GL shaders, but I also held out. At the time that I first did Haiku, WebGL was not widely supported, and so I was concerned that I needed a fallback to JavaScript. At least in Chrome, about 8 months ago, we finally reached the point where actually there's a software renderer called SwiftShader that's now previously was a background download that would happen if your machine, for whatever reason, didn't have a working GPU. You would download a GPU-based renderer. We've recently started bundling that inside of Chrome, and so now basically Chrome can pretty much always do WebGL. This is less true with the other browsers. So one of the reasons I've kept in that intermediate step to JavaScript is that it actually falls back to that if it finds it yourself on a system that doesn't have it. But that doesn't answer your question, which is could I do better if I skipped through? Possibly. One difference is that the shader language is actually closer to C, and it has a number of the flexibilities that are born out of it being C, whereas JavaScript has a number of constraints on it. It requires that there's no irreducible control flow. And so there's differences in terms of what you can do in each of the two. I could probably make things a little bit more flexible if I cut out that middle layer. On the other hand, there are places where I actually still use the JavaScript implementation even for the animated haikus. For example, some of the interactive haikus, basically what happens is that I run the shader for every pixel through the GPU, but in terms of interacting with your keyboard input, I pretend that there's a single pixel, and I run the JavaScript version of the haiku for that one pixel. It is possible for me to route through the GPU and get the answer back, but one of the things that's historically been problematic is because the GPU and CPU in a lot of systems actually use separate pools of memory, the communication time reading back from the GPU to the CPU can sometimes be problematic. In order to actually read back state data from the GPU, you typically have to have the CPU basically wait on the GPU. And during that time, you lose some opportunities to do work and be responsive. That said, it's getting GPUs are generally getting better at this readback not being terribly expensive, and so it's probably possible if I tried it. A related place where I'm also using the JavaScript is for sound. I render a single pixel and use that to get the waveform out. That one I'm actually a little bit more worried about going round tripping to the GPU because I'm running a single pixel, but I'm running that pixel for several units of time, because when you're providing sound data to the sound card, you don't provide it one sample at a time, you provide an entire buffer. And so I have a time slice that I have to run that over. And the JavaScript engine for that tight loop will optimize the code that I get and then and hand it over. If I went to the GPU, I suppose I could structure it so it sends a different shader so that each pixel position gets the audio data, but then I would have to generate yet another variant of the shader that knows how to put the time information spatially. So it's possible. Another possibility that's coming is WebAssembly is now available actually in 4 browsers, and so I may look into seeing what the performance is like if I were to re-implement things on top of WebAssembly. The downside is I would be moving from this massively parallel GPU to the CPU, which is often more powerful in terms of what you can do with each individual core, but it typically doesn't have the same level of parallelism. But it might unlock the possibility of something that's a little bit more like a traditional fourth. So some interesting possibilities and trade-offs there. Or I might spin up something completely separate from fourth haiku, because at this point, fourth haiku is pretty heavily tied to the GPU. It's sort of that's the nature of most of the programs, that they're working around these limitations of the GPU. Thanks. All right, everyone, we're going to be back at 1 o'clock.